rigor. Engineer Urban Biosphere Infrastructure, Meta Systems Blueprint. Executive Summary. We propose a coordinated multidisciplinary program to develop urban biosphere systems. Integrated building scales, forest installations, engineered for air purification, cooling, water management, and resilience. Leveraging vertical green infrastructure and novel biofiltration, this program will pilot large trees and moss/algae living filters on buildings. We recommend a lab-to-flagship roadmap. Bench experiments and simulations, Phase 1, contained pilot installations, Phase 2, then city-scale demonstrators, Phase 3. This blueprint outlines critical technical modules: structure, root/hydrology, vegetation/biofilters, monitoring, fire/safety, governance and financing strategies, and research priorities in a scaffolded prompt chain format for iterative AI-assisted design. Governments, developers, investors, universities, and insurers each have roles. Government and city agencies provide policy enabling, for example, special permits, building code amendments, incentives, and funding. Private developers and infrastructure funds provide capital and implementation expertise. Multidisciplinary research teams, engineering, arboriculture, ecology, will execute experiments. Insurers and risk managers will structure coverage as systems mature. Philanthropies and NGOs can seed early-stage prototypes. The 50 to 100-year legacy vision is an urban carbon forest, networks of living megatrees in cities that continuously filter pollutants, cool and humidify streets, retain stormwater, sequester carbon, and provide habitat and human well-being. Early 5 to 15-year goals include demonstrating safe, maintainable vertical tree installations with measurable air/water benefits. The following sections detail modules and meta prompts to achieve this vision. 1. Technical components, structural and geotechnical systems. Overview: supporting large trees, trunks, crowns. On buildings requires hybrid framing, bracing, and damping. We envision steel/timber trees or frames anchored to buildings and ground, anchors, piles, or outriggers that bear trunks and lateral loads. Instead of hung sequoias, impractical, design uses distributed ground support plus cable nets plus dampers so trees can sway safely. Recent studies confirm trees on buildings are viable only with special design. For example, Abusef et al., 2023, developed a 4-stage framework: sites, studies, techniques, maintenance, precisely because failure risk is high. 16L, 199 to L207, 18L, 123 to L130. Green roof and sky garden standards, intensive versus extensive, typically allows small trees, 16L, 199 to 207. But giant trees exceed usual loading, so new engineering is needed. Key requirements: load capacity, support soil, water, tree, trunk, weight, plus live loads, wind. Roof structures need reinforcement, high live load capacity, or added support columns. Preliminary analysis should ensure greater than 5 kilonewtons per square meter sustained load capacity, including saturated substrate, plus dynamic factors for wind. Wind dynamics. Tall trees can sway meters in winds. We will instrument small prototypes to measure sway and develop dampers. CFD studies, for example, green wall fires, 36L81 to L89, show foliage delays failure but channels smoke. Similarly, vegetation increases drag and flexible support must be designed, for example, tune mass dampers on trunks to limit resonance. Attachment system. Trees may be fixed to frames that include slip joints or hinges to prevent tree injury. Multi-point anchors, cables distribute lateral forces into building skeletons. Connections will allow controlled flexibility, some lateral movement, to absorb gusts. Geotechnical footing. Where trees tie to ground, podiums, or plazas, Root corridors must be deep and stable. The foundation design, for example, soil cells or caissons, must resist overturning moment from tree canopy wind loads. Planting modules like structural soil and root cells, 90% void space polypropylene, are proven to support paving while hosting roots, 9L127 to L134. Similar engineered mixes will be used under planters. Safety and redundancy follow BSV structural guidelines and fire codes. Use redundant supports so no single anchor carries entire load. Install load monitoring sensors on primary anchors. Include vertical fire breaks or irrigation to prevent fire climbing between trees. Insight: trees on buildings must be designed with maintenance and failure in mind. Abusif et al. Warn that poor planning increases risk of failure and maintenance costs, and emphasize perennial maintenance planning, 16L55 to L63, 18L123 to L130. We will mandate frequent inspections, e.g., fortnightly arborist checks, 18L123 to L130. Advanced warning devices, tilt sensors, and fail-safes, controlled crown lowering actuators, as critical safety features. Root zone architecture, soil volume and composition. Large trees need large, well-aerated root volumes. Urban soils are typically too compact. From Allaudet and Basak, 1994. We will use engineered planting media, mix of mineral soil and organic matter, with porosity greater than 50% and structural support. Crushed stone or structural cells beneath to bear loads, 9L107 to L115, 9L130 to L139. Based on urban forest studies, planters should provide at least 5 to 10 cubic meters of substrate per mature tree as a starting point, similar to large street tree planters. Engineering trade-off from recent research: porous, stone-heavy soils boost infiltration but can stunt growth, 11L95 to L104. We expect to tune mixes for each species. Infiltration versus vitality. A 2025 study found a classic trade-off. A multifunctional engineered soil, stone-rich, reduced runoff sharply, but yielded 2 to 3 slower tree growth versus rich soil, 11L, 95 to L104. This indicates we must balance stormwater capture with oxygen and nutrients. We will design dual-layer substrates, an upper mineral peat blend for roots, approximately 1 meter deep, and a lower structural aggregate layer, approximately 0.5 meters, for drainage. If green walls are used, separate filter layers ensure roots don't smother each other. Water/O2. Delivery: roots must avoid waterlogging while retaining moisture. We will implement subsurface drainage mats and aeration channels. Overflow pipes and valves will prevent saturation. Periodic flushing cycles, via IoT-controlled valves, will ensure sediments don't clog. Sensors, moisture, O2, embedded in root mix will monitor status. Oxygenation can be enhanced with periodic aeration pulses, for example, airlift pumps, if automated irrigation is used. Microbial support. We will inoculate substrates with beneficial mycorrhizal fungi and bacteria to support tree health. Closed-loop graywater usage, filtered and UV-treated irrigation water, can nourish microbes without chemicals. Short-term lab experiments, Phase 1, will compare soil microbiomes in different substrates, as microbial health is critical to long-term root function. Hydrology and water reuse, closed loop. Stormwater capture. The system will capture rain for immediate use or storage. Based on green roof research, blue-green roofs, with additional storage layers, can retain approximately 60 to 80% of runoff, 20L77 to L85, 20L117 to L124. For example, an Italian pilot, Palermo BGR, de-peaked flows by 80% and captured 61 to 77% of daily rainfall, 20L77 to L85. We will incorporate on-roof cisterns or bioretention zones, blue layers, under tree planters. Valved outlets allow retaining water for watering rather than rapid release. Irrigation system. A smart irrigation network, sensors plus AI control, will supply water only as needed. We envision an AIoT system with local weather forecasts and soil sensors to maximize retention. A 2025 pilot using ESP32 controllers and ML algorithms cut irrigation 13%, while boosting plant growth 3.3, 27L 59 to L 67. We will adapt such smart graywater reuse systems, targeting approximately 40 to 60% potable water offset, common in green building ratings, 22L5 to L8, or when graywater from sinks/toilets will be biofiltered and stored for irrigation after treatment. Rainwater harvesting will top it up. Water quality. Captured runoff and graywater will be treated, sand filters, UV, constructed wetland stage, before use. Sensors will check nutrients, pH, contaminants, for example, heavy metals from air deposit. Overflow from roofs will drain to enhanced infiltration areas or stormwater network via filter pass, also capturing runoff pollutants. Trees naturally remove fertilizers and heavy metals. 53, 13, 1 to L 138. 55L 13, 1 to L 139. EL. Measurement and targets. We will monitor inflow/outflow volumes and quality. Key metrics: percent runoff retained, target greater than 70% for moderate storms, evapotranspiration fraction, and water reuse versus total. A water balance model building on LID principles, 21L 5852 L 593, will guide design. Experiments will measure infiltration, infiltrometer versus plant growth in different soil profiles to optimize the soil depth versus retention curve. Vegetation and biofiltration design. Tree species and staging. We advocate a succession of species from small to large. Initial pilots, phase 1 to 2, use hardy, wind-firm species, for example, young oaks, maples, cypresses, with known rooftop performance. Giant sequoias or pines are too large for early phases. Instead, we simulate large canopies with clusters of mid-sized trees. Over time, as confidence grows, we can trial select flagship trees, like mature conifers, with immense canopy. Species will be chosen for deep roots and slow growth to minimize failure risk. Non-invasive root habits, drought, and pest resistance. Canopy ecology. Beyond shade, foliage serves as an air filter. We will layer plants. Tall trees provide shade/structure. Understory shrubs and climbers, for example, ivy, Virginia creeper, cover trunks and walls. Mosses/lichens form a living skin on paved surfaces and facades. A separate biofilter layer, for example, living moss mats or biochar modules, will be installed on breezeways and sidewalk facades. Unlike supporting structure, these filters are lightweight and targeted for air cleaning. Moss/lichen filters. Recent experiments confirm mosses excel at PM capture. One trial found moss panels trapped approximately 45,000 particles per square millimeter over months, approximately 50% being ultrafine, less than 0.5 micrometers, 31L 69 to L70, 31L 88 to L94. Moss species, for example, Homolothecium or Grimmia, will be grown on vertical panels or lattice. We will quantify removal efficiency, particle counters up/downstream, and VOC absorption in pilot experiments. These biofilters, for example, modular moss trees, are easily replaced/sterilized, avoiding loading structural layers. Microalgae photobioreactors. As a supplementary measure, building facades can host algae bioreactor panels for CO2 capture. A 2025 study showed chlorella cultures in window box photobioreactors yielded approximately 175 milligrams per liter per day biomass, 34L 339 to L 347, capturing CO2. We will pilot small algae panels, glazed tubes, or light-exposed walls to sequester carbon and produce oxygen/biomass. For example,